Okay, so in the last session, we were looking at an interesting model that had interesting complications to do with contact and looked at different settings to get it working and what would happen if you have the settings wrong and so on. In this session, we look at interference, but something that's supposed to be easy to model, but there's so many complications that things tend to go wrong a lot. So let's start with just showing the model what we'll work with. So initially there's no interference fit, we'll add that later on. So I've just constrained this to bare minimum to get this to be fully stable. And I've set up contact between these, use default settings, material properties undefined. Let's run the model and see what happens. So we expect zero stress state for this because there's supposed to be no interference. Here's the model run completion. We look at the contact status first. So with the default setting, it decided to make contact from the outside to the inside. This, in this case, was simply because this was the first contact body defined, which I'll show in a bit. Then if we look at the von Mises stress, initially there's nothing because that's the initial state, and then we see a really weird stress state. And bear in mind, this is an MPa. So something that's supposed to be perfectly in equilibrium initially, zero stress, already says there's a 16 MPa stress in the model. Okay, so let's first see what happens if I project stress free. So this is due to some small overlap possibly of a mesh somewhere. So let's just, before I do the interference fit and stress free and so on, let's start with my contact table. Let's swap the contact around. I want to make contact from the inside to the outside. For a lot of the settings, it'll make more sense if we start adding smooth surfaces. It doesn't matter too much what direction we're doing. So let's just do this at least. So I fix second to first, so the pin will make contact to the plate. We rerun the analysis and there will probably be a slight change in the answer, but not much. Look at the result. And it's now 18 MPa. I think it was 16 before. Okay, so let's start with a cleanup first. Let's try to project stress-free. I just want to see what the effect would be in terms of the initial stress state. So I just activated stress-free. I run the analysis again. And I see a stress state of 2e minus 4, 3e minus 4. So that's less than 1 kPa stress. So that project stress-free wasn't necessarily perfect, but it was at least pretty decent. Okay, so now let's go back and say, I want to deactivate that again temporarily. We'll switch this on and off as we go through the different possible settings. So the first thing is I want to physically enlarge this. I want a 20 micron overlap. So what I'll do is in this case, let's just select the contact body, the pin, and the diameter is 10. So I'll just scale it up with a certain factor to get it to a 20 micron interference. So I go to move nodes and I scale them. And that center point there is at 0, 0, 0. Typically in models, that won't be the origin, so you'll have to scale slightly differently. In this case, the scale factor should be 1.002 in the X and the Y direction. So move the nodes all selected. And when I clear this and zoom in there, you'll now see there's a 20 micron distance. So let's measure that distance to check. And from there to there, 0.02. The model is in millimeters. Okay, so if we rerun the analysis without making any changes. Okay, so a bit further away, it kind of makes sense, but at that interference, but I can see something is happening, but I'm definitely not happy with the answers. So as I go in the circumference, I expect to see not necessarily constant stress, because that would require this to be a circular section so that it's symmetrical, but still some kind of an oscillation, at least with very minor changes from the center to that. So those points should be the same, and this one maybe a bit higher or lower depending on how the structure behaves. So at least it's a reasonable first order answer, but it's definitely not great. Let's just take a snapshot of that number over there so that we've got a reference later on if we start tweaking the model. Okay, so the question is, why do I see this kind of a stress state? I'm making contact from the inside to the outside. And what probably happens is, because of the way it deforms, these nodes slightly slide sideways, and then it makes contact on that faceted section, or this faceted section, instead of that initial perfectly smooth shape. So let's go back and say, I want to change the plate, because I'm checking from the inside to the outside. I want to change the plate to a smooth representation. So the smooth representation, the default setting should be okay. We can maybe switch that one on just for a minor improvement. But what this physically says is any angles greater than 60 degrees, so that is 90-degree change. Anything over 60 degrees, it'll treat as a sharp corner. Everything else, it'll try and fit a smooth surface through. So that's it. No other changes, and we're on the model again. Can we look at the stress state again? And now I see something is not perfect, so there's still a slight variation there, but that can be due to the element distortion and shapes and so on. But this is an order of magnitude better than the previous result. I take that snapshot from before, it changed from 420 MPa to 330 MPa. So bear in mind, I'm not saying that this is correct because the mesh is not necessarily fine enough. I can see that simply because I changed from, let's say, about 330 to somewhere around a bit over 200 MPa in one element. So to do this better, I'll have to model with finer elements in the circumference and, well, circumference and radially, ideally. But still, we've got a reasonable first order answer. Okay, so let's take a snapshot of this again, because this I expect to make more sense. So we'll use this as a reference for further changes. Let's look at it from the top and just see some of the characteristics. So see there's no overlap over there. If I close the result, you'll see there was an initial overlap. So as part of the run, the moment it opened, it closed that gap. Okay, so further improvements we can make, bear in mind we had that slight issue of slightly strange stress distribution initially. So let's say I want to use project stress free. That'll mean we'll move this node back to there, and that's not what I had in mind. So let's just see if I do this. Now, just to prove that that's the case. By project stress free, I should again see very close to zero stress, and the nodes will still tie up after the run. Okay, and look at the stress. So there you can see it's projected. And if I look at the stress state, again, that's pretty much zero. If I look at the numbers, it's something E minus 10. So it's even lower than before. So it's a really, really low stress. Okay, so the project stress free work, but now I've lost my interference fit. So let's go back again and say, but how can I combine this in some way to still project to get, in other words, a perfect initial 20 microns and then run the analysis correctly. So what I can do is, let me just show, I've got two tables, one ramp up, which simply says whatever I initially have starts at 0, and at time 1 it ends at value of 1. I've just created the ramp down as well, which starts at 1 and ramps down to 0. In most cases, if we have loads, we'll use some kind of a ramp up kind of an equation. In this case, what I'll do is I still have the project stress free on. And now I activate interference fit. Now, the interference fit and overlap would be negative. So I say initially there's a 0.02, which is that 20 micron overlap that I initially want. And I link that to the ramp down table. So initially it'll start at that value, but then I ramp down to 0. So this will be easier to understand once I run the model and have a look at the results. Okay, so it kept that overlap, but what it did was, if I plot the contact status in this case, so there you'll see pretty much all around it's in contact as expected, but it's making contact 20 microns into the part and projecting stress free to that location. And then I say take away that interference. In other words, it forces that back onto the surface. So if I go to the next step, you'll see that it's no, it doesn't necessarily look like it's perfectly in contact, but the reason for that is this slight sideways offset and it makes contact against that spline. Okay, so if I now look at the stress state, very similar to before. Let's take this again, look at the numbers. So the maximum is exactly the same, the minimum slight change, the pattern not exactly the same, but very close to the same. So come on, it keeps on jumping around. So there on this side and over there, there's a bit lower value, and we still see something like that, but that I expect is more to do with the quality of the mesh than anything else. Okay, so there was a minor refinement that we could implement in this model. Now the question is, why would I want to do this? So in some cases, for whatever reason, I want to model that interference by modeling an overlap. And this can be used to clean up a model. I'll show you a nice example of where this is critical if this is what you're interested in a bit. So let's step back a bit and say, we're happy with the answer, but let's say I want to model using interference fit without an overlap. So what I'll do in this case would be, I'll change this slightly. I'll say, again, interference fit, but instead of a negative value, I'll make it a positive value of 0.02, but then I ramp it up. So what this means is initially, it'll make contact perfectly in the correct node location, which means we'll project the node to the initial so that there's no overlap, but then I cause an interference fit, which will visually be seen as a gap of this much. So if I run the analysis again, so see there in that initial step, it projected it, so it does not keep that overlap, but this is the zero stress state. And if I zoom out, go to the next step, you'll see the stress is pretty much the same. I'll just get this one again. Look at the scale, exactly the same. This one was just that slightly different one, which I said is had to do with the way we project it. Now, this is the difference. In the other model, these two are exactly on top of each other at the end of the run. While using this method, I've projected it to start as if they're perfectly in contact, and then I add an interference. What interference fit in this case is, so let's plot contact status to show. So this node is in contact, even though there's a gap. And the reason for that is we're saying this node makes contact 20 microns before the other face. In other words, one way of looking at this would be we're forcing some kind of a 20 micron shim in between these two, but we're not modeling it on, or we don't see it. So in terms of the effort to set this up, this is a lot less effort than anything else. So let's go back to the original model, the one that did not have an interference fit. So I'll use that one. And let's just save it on a new name. So this is the initial one. There wasn't an overlap. And the first thing I want to do is I want to project stress free to ensure that there's no overlap initially. And then in the contact table, I then need to define, okay, let's just change the direction again, second to first. And I specify interference fit of 0.02 and I ramp that up. Okay, so what this means is initially, if there was any penetration or small gaps, it will clean that up perfectly, and then it will force open that gap. So we run the analysis. And I don't expect a perfect answer. I'll show you in a second why. Okay, so we still have the same issue as before, and the only reason then is we did not specify the plate as smoothed. So the plate is smooth as well. So this one is smooth. This makes contact on that perfect circle, in other words, the fitted spline. This initial projection perfectly onto that spline surface, and then we open up that gap. That's all that we effectively said. So if I run the model now, I should see the same result as before. Okay, so I get the same kind of pretty picture in terms of what the stress distribution is. Okay, so this is on a perfect model where it was pretty easy to get this working, whether I use the interference fit physically meshes overlapping by 20 microns or whether I projected, or pretty much all of them gave either the same answer or very, very close to the same answer. Now, let's first show a good but more complex mesh. So this is a second order Tet mesh, and this one is, there is an overlap. It's actually not that easy to see because the meshes do not tie up. So what I'll do in this is, again, I'll specify the plate. I'm not going to run this. If you want, I can, but it'll make very little difference. So I just make it smooth again. Even if it's second order, you get a slightly better answer. And I just change the contact direction. So that it's the pin that makes contact to the plate. So that's again equivalent to the previous run. So I run the analysis. And I expect to see very similar stress pattern. The actual numbers might differ a bit. Okay, so look at the stress. And I see a pretty decent stress distribution. Just for reference again, previously we saw about, let's say, 330, just below 330 MPa. Now I see 375. Okay, so that's about a 15% difference. Okay, so why do I expect to see this? Because firstly, it's second order elements and it's a slightly finer mesh. So if I remesh the other one, I expect to see very similar kind of behavior. So at some point, once your mesh is fine enough, this value should converge. Okay, so to be honest, in most cases, we're not that interested in von Mises. We're interested in the radial component of stress, and that at least should make a bit more sense or be a bit more comparable between the different methods. Okay, so that said, this model, as I say, I did not use the interference fit feature. So see, the interference fit is off, it's physically overlapping, and then it forces it back onto that. So let's see if it's visual. So that's the initial state, and you should see there's a slight movement radially outwards and radially inwards between the initial and then the stressed state for that interference fit. Okay, so the second one is exactly the same model, except it was meshed in a slightly different way. And I did not spend any time and effort to try and get a bad mesh. I actually tried to get it a good mesh, but it was just meshed in a slightly different way. And I run the analysis again. So to do this again for equivalency, ensure that the plate is smoothed. And for the contact, instead of the default settings, I just go from default to second to first. I run the analysis. Okay, and let's first look at the contact status. So that makes sense. And also just want to show if we step on, you see that slight radial movement from the initial to the final state. So we're modeling exactly the same interference. We've used exactly the same parasolid file for the two. If I look at the equivalent of stress though, it's okay, it's not great. If I switch off the analytical, the smooth contact, I actually see a slightly worse behavior on the outside, but still the number differs from before. More or less the same mesh size. If there's differences, it's very minor. So at least it's vaguely making sense. But what we can do here is let's just check whether the initial, that 20 micron was accurate enough. So what we'll do is again, we'll project stress free. And then that projects stress free. I want this to be at minus 0.02. And then I'll use that same ramp down one. So initially I'll project to that amount of interference and then open up that or remove the interference. So let's just, before I run the model, let's just take a snapshot of the results again. So again, bear in mind, we expect to see, what was it, 375, I think, for this similar mesh. Now I see slightly higher. And if I now run with the new settings where I project perfectly onto that exact distance, okay, so it's still a bit higher than the other one, but again, bear in mind that it's not a perfect mesh that we started off with. Okay, so if I just the last one show you, if I do not smooth the plate for this one, I didn't show it on the other mesh, but it happened the same. I need to switch back off the interference fit in the projection. Sorry, this one rather. The previous state mesh, even using this settings, gave okay answers. I think I just need to change the direction. Let's see if it converges. I don't think it will. Okay. I either need to increase the number of iterations or I just need to switch this back to default. So again, it's making contact outside to inside. Yeah, and we get this kind of garbage. So we're back to about 600 MPa, which is ridiculous, but from the pattern, it's pretty clear that something is severely wrong. And if we switch off the pin, I expect to see some weird stresses inside over there. Okay, so all of this is due to slight overlaps in some regions and some slight gaps initially due to that slightly bad mesh. Now, as I say, the easiest method is instead of what we're now trying to do, projecting to that initial 20 micron interference, let's just do the opposite. So just again for comparison, I'll use second to first. I'll ensure that the plate is set to smooth. And then I'll project. Let's say it over there. So still project stress-free. But then the final step is I specify interference fit of positive this value. And I ramp that interference up. Okay, so at this point, the slight overlap, it will be projected so that it's perfectly on the right location. And then when we run the analysis, I again expect to see a small gap opening up. Okay, so what's the advantage of the method with a gap, the normal interference fit method? It's a bit easier to set up, but the main advantage is if you're not certain what interference you need, it's possible to run a series of different interference fits, effectively using a table like we've just done. And we can see what the stress state would be as a function of that interference fit. So let's just go back to the last step. So again, we have that same stress as before, and it's not that clear, but there's no overlap in this case. Sorry, there's small gap supposed to be in this case because of the way that we've modeled this. Now to see the effect, let's say we increase the interference fit a bit. Let's say 0.05. And instead of doing it in a single step, I'll just change the load case and say let's do it over 5 steps. So we'll start with a 0 interference and then 10 micron, 20, 30, 40, 50, and we can see all of those results then in one run. Now, since this is close enough to linear, I don't expect to see anything else, but if there was plasticity that could occur in the model, in that case, I expect to see a difference. No, I didn't run it again, sorry. That should run a bit slower. Okay, so the first step is complete. So look at the results now. Equivalent of stress, and there you can see, let's say 200 MPa more or less for a 10 micron. Then as it runs 20, 30, now the pattern doesn't change, but the numbers does, simply because that gap is increasing. Okay, you'll also see if I zoom in, look at the deformed shape. So that's where that gap is physically opening up. There's a 20 sorry, at the end of this, there's a 550 micron gap. It's just not that clear with second order elements. Okay, so that brings me to the end of the session. The intent of this was just to show you how to use the interference fit option. This option, in other words, in the contact table between body pairs, and being able to ramp that up or down depending on what you wanted to do further with analysis. Okay, so my experience in general is if you try and physically model interference, I make this pin, argument's sake, 20 microns larger than it should be before I run the analysis, I tend to really battle to get decent answers. So it's a lot easier to use one of these two methods, where you either project to the, so in other words, no overlap initially, and you project to that, and then run the interference with a 20 micron argument say gap, or the alternative is to project to that minus 20 microns in this case, and then ramp that back down to 0. So that's slightly easier to visualize or to explain to somebody, but the answer is pretty much the same in terms of stresses. Okay, thank you. Any questions?